Hi, this is a lecture on equation writing. It's a resource lecture, and if you understand the lecture, it will be invaluable for your study of chemistry. As a matter of fact, chapters 10, 11, and 12 are the central set of concepts for chemistry. It's the structure. Understanding how to write an equation and then understand the molar relationships within the equation are going to be invaluable for your study of anything in chemistry, from acid-base chemistry to solubility to thermodynamics, kinetics, etc. Equilibrium. It's all going to be involved with the equation writing and the skills that you need for equation writing. So let's begin the lecture right away. There are 5 types of equations that you're going to be looking at, and we'll start with single replacement. All right, the first of the 5 types of reactions is going to be the single replacement reaction. Another set of texts might say single displacement. And either displacement or replacement is descriptive enough to be used. You're replacing either the cation or the anion. There's actually 2 types of single replacement. There's those types that replace the cation and that which replaces the anion. And we'll look at those very closely when we actually begin. The next type is double replacement or double displacement, and that's where if you think of 2 compounds, or each compound has a cation and an anion, so you have 4 total ions, 2 cations and 2 anions, and it's simply they change partners. So the cation changes partners with the other cation, and you end up with 2 different compounds. And we'll again look at that very closely in the coming slides. And there's 3 types of double replacement. 3 examples of double displacement or double replacement. Then there's going to be the combination or synthesis. And the combination or synthesis is going to be where you either take 2 elements and form a new compound, or 2 different compounds and form a new compound. But the idea is that there's going to be 2 reactants and then 1 product. Decomposition, you're going to have the reverse of the synthesis, where you'll have 1 reactant and then 2 products, where you actually break things down as opposed to putting them together. So instead of a synthesis, it's going to be a decomposition. And then the 5th type is going to be called combustion. Now, combustion is simply one thing, where you take a hydrocarbon and you combine it with oxygen, and you will produce carbon dioxide and water. The thing about a combustion reaction is that they are rarely pure. In other words, you get a lot of side products. You get carbon dioxide and water, but you also get other things, because you have hydrocarbons that are left over or uncombusted, if that could be a word. So hydrocarbons are a little funny that way. You get a lot of intermediate reactions left over. So first we're going to look at single replacement. Single replacement, again, is where you have an element in a compound and you're going to produce an element in a compound. And that's how you recognize it. You have an element, which is A, and then you have a compound, which is Bx, and you take the A and the B exchange, or the A displaces or replaces the B, and you wind up with you wind up with AX and then plus B. So the first kind we're going to have A, B, C, and D. And the first kind we're going to have is when you have an active metal. Here are the active metals. Okay, you're going to have an active metal in water. And then you're going to kick out the hydrogen, and you're going to produce the OH. You're going to have actually the metal OH, so magnesium hydroxide, for instance. A base is defined by the presence of OH. That's why I say base plus hydrogen. Now, just be careful of this, that the active metal has to be more active than the hydrogen. But be careful. Let's stop. Well, we're not going to stop because the next slide will show you. But look into what it says. The metal from lithium to sodium, so it'll be sodium, potassium, and lithium, will replace hydrogen from acids and water. From magnesium to lead, they will replace the H from acids only. So in terms of the activity series, let's just stop the tape for a minute. I want to talk about this a little bit further, so hold on. So even though lithium, potassium, calcium, sodium, magnesium, aluminum, zinc, iron, and lead are all more active than hydrogen, only lithium, potassium, and calcium replace the hydrogen in water. And then they all, from lithium down to lead, replace the hydrogen in an acid. So that's a caveat that you've got to be aware of. The table on the left, table 2, is from your book, and the table on the right is from the internet. It's a little bit more complete. And we'll come back to these tables several more times. Now, the first problem we're going to do, the first practice problem, is sodium and water. Now, according to the table and the little black box on the right side of it, sodium will replace the hydrogen. So it's going to kick out the hydrogen. And remember, hydrogen exists as a diatomic molecule as well as others. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all exist diatomically when they're alone. So, the sodium is going to kick out the hydrogen, and you're going to be left with a base, sodium hydroxide, and H2. Now you have to balance the equation. Balancing is very simple. I'm not going to really spend a lot of time showing you how to balance. It's simply an accounting method. There are some tricks. For instance, if a polyatomic ion exists on the left and the right, then balance the polyatomic ion, not the elements that make up the polyatomic ion. Now, often in a single and double replacement, write H2O as HOH. So you're writing the polyatomic ion. So hydrogen is on the left and hydroxide is on the right. That's how you're actually balancing it. You're balancing the hydrogen, but you're also balancing hydroxide. Now, this is another, I kind of started off kind of slowly, and we have we're going to do another example of an active metal and water. Now remember, there's only 3 elements on that table that are going to be able to replace the hydrogen in water. And another one of them is calcium, which we'll see in lab. So calcium will come in and replace the hydrogen and produce calcium hydroxide, which has a lot of industrial uses, and it's a fairly common substance, calcium hydroxide, only slightly soluble in water, but there it is. It's calcium hydroxide plus water, and that's how you balance it. So you're balancing 2 OHs and 2 Hs, and it's simply easier to balance when you write the water as HOH in single and double replacement problems. All right, we're going to do another one where again you have the active metal and you're going to put it in. Now, I may do some problems, and not every problem that I do can actually run. Some of the problems that I do, I'm not going to be able to, are not going to simply run. They're just simply predicting products, and that's a very important distinction between problems that I predict the products that the reaction will actually happen and problems where it won't happen. I can still predict the products. Just because the problem doesn't happen or the reaction doesn't run doesn't mean I can't predict products. You only predict products in this theoretical framework where you have a list of rules and a combination of elements and ions, but the real test comes in a laboratory where you see what happens with the combination of reactants to see if the products are actually formed. And we say that the reaction ran. If the reaction doesn't run, then we say, when you say no reaction, you say, colloquially, you say, well, the reaction simply didn't run. No reaction. So let's look at another type of reaction where I'm going to put an element with an acid. Now remember, there are many more elements that will replace hydrogen in an acid relative to hydrogen in a water. Now, why is it more difficult? This is a question. Why is it more difficult to replace the hydrogen in water as opposed to the hydrogen in, say, hydrochloric acid? Why is it more difficult in the water than the hydrochloric acid? Let's look at that and see maybe if we can figure that out. Why is the hydrogen in water more difficult than in an acid? Okay, let's look at an active metal in an acid. This is going to be another example. All right, well, what happens? Well, the active metal is going to come in and displace the hydrogen. All right, simple enough. And then you're going to form a salt of the strong acid and hydrogen gas. What do I mean you're going to form a salt? What does that mean, a salt? Well, basically a salt is not an oxide. It's made of two ions, a cation and an anion, and they are not hydrogen, hydroxide, or oxide. Generally the case, as you can see. Oh, we have a guest this morning, very early. Gosh, 6:25, and he's here to make up a test. I am impressed. But let's get back to this in a moment. Be right back. So let's look at some examples of active metal and an acid. This first one, calcium and hydrochloric acid, you're producing the salt of a strong acid, which is calcium chloride. And we're going to be talking about calcium chloride later on relative to solubility. Why is calcium chloride used as a salt for roads as opposed to sodium chloride? There's two reasons. Why is calcium chloride used? Why does your father prefer to use calcium chloride, or let me rephrase that. Why should he use, if he doesn't know, why should he use calcium chloride at home on the sidewalks if there's snow and ice on the ground, as opposed to sodium chloride? There's two reasons why he should use calcium chloride. Calcium chloride is a little bit more expensive, but a little goes a longer way. So the next one is going to be sodium and sulfuric acid. Let's hold on for that. Very exciting. Be right back. All right, this next one is sodium plus sulfuric acid. Make sure you consult the chart. This is going to be extremely violent, extremely violent. It would almost explode on contact. It would be so violent. You would need sulfuric acid to stimulate maybe some kind of vigorous reaction with, say, lead down at the bottom. But sodium, it would be too violent. You really couldn't do it in a regular classroom. It would be just too violent. If you use calcium, it would be violent too, or magnesium even, depending on the concentration. So there it is, sodium plus the sulfuric acid. You're kicking out the hydrogen, and you are creating sodium sulfate. Why is it Na2SO4 because you have +1 sodium and -2 sulfate, and then you have plus the hydrogen and you balance it. Let's do another one where you have an active metal and an acid. And we'll be doing these as we work in the laboratory. We'll be doing some of these reactions. Zinc and hydrochloric acid, very popular combination. You're producing, well, zinc is going to kick out the hydrogen and make zinc chloride and hydrogen. So if you look at your chart, you'll see that zinc is above hydrogen, so it's more active. So it will displace the hydrogen and produce the zinc chloride, because that's what's left over, because it's HCl. So the reaction would be zinc plus 2HCl yields zinc chloride plus H2. Now, again, you could look at this in various ways. You either look at it as one particle to two particles to one particle to one particle, or 1 mole to 2 moles to 1 mole to 1 mole, etc. All right, let's begin with another example of an active metal and an acid. The next one is going to be magnesium plus perchloric acid. Now remember, perchlorate becomes perchloric, so it'll be HClO4. And you'll see that the material is going to be more active than hydrogen, so the magnesium will displace the hydrogen and produce magnesium perchlorate and hydrogen. Now, I want to draw your attention to a very simple fact, and you can look back at this later on. So let's talk about this for just a moment. In this particular reaction, magnesium is solid, the acid is aqueous, the salt generally is going to be aqueous that I produce, and then you have hydrogen gas. Now, hydrogen gas is molecular, and the gas will bubble off. And as you reduce the amount of product, you want to produce more product until there are no reactants left. So look carefully at those quantities in parentheses. Solid is in parentheses, AQ, aqueous, meaning it's a water solution, and also the G, which means gas. So the state in which the reactants and products are in are going to become as the year progresses. Not necessarily in Chapter 11, although we will look at that a little bit, and I will talk about that from time to time. But remember, the main theme here is predicting products, predicting the chemical reaction, and writing a balanced stoichiometric equation. Looking at the state, dissolved, gaseous, solid, liquid, etc., will become important as the year progresses, and we're going to dabble with that for now. You'll see that some of the later equations don't have any states next to them, because I want you to concentrate on just the straight predicting of products and the writing of a stoichiometric equation. Oh, I'm not losing my mind. Okay, all right. Magnesium and nickel-3 perchlorate. If you look on the next slide, you'll see that magnesium is above nickel in the activation series. So magnesium is 1, 2, 3, 4, fifth from the top, and then nickel is just below the middle. So what will happen is the magnesium will replace the nickel, and you'll form magnesium perchlorate plus nickel. So the cation that's being replaced turns into a neutral atom, neutral element. Now, I'm going to do a series of problems that is going to start with number 8 and see what you can do with them. I'll just kind of let things go and see what you can do. All right, be right back. All right, the next one, you have iron plus tungsten 1 hydroxide. Now, you have to know what the cation is going to be, and in this case, we're going to say that it's going to be iron 2. So you have iron, that'll become iron 2. That's going to displace or replace the tungsten 1. So then you'll get Fe plus 2 tungsten 1 hydroxide yields 1 iron 2 hydroxide plus 2 tungstens. Notice that the metal that was replaced, the tungsten, becomes neutral, and the iron begins as something that is neutral. Next, barium plus sodium chloride. As you go down that column, the barium is actually less active than the sodium, so that reaction will not run. That reaction will not run. Next, we have a replacement of halogen. See, the Y is going to replace the X, so you're going to get By plus X. So the most active halogen is fluorine, and then the least active halogen is iodine. So I'm going to let the next series run, and you'll see that things are replaced. Now remember, one caveat, that the hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, iodine, they exist diatomically. So it's going to be Cl2 and Br2, and then you have to balance everything. Okay, so I'll just let this run until the next series, till the double replacement begins. So there's going to be 4 problems on this page. Some will run, some won't run, and it'll be consistent relative to all the rules. So you can see that the chromium is going to stay chromium 3, but the reaction is not going to run. So the prediction of the products, you're predicting that no reaction will occur, so you don't have to run it. The next one, the bromine plus the potassium chloride, remember, when the halogen is alone, it's written diatomically. I'm going to change the timing so the next 3 slides will go very quickly. The next is going to be a double replacement reactions, where A is a cation, B is an anion, C is a cation, and D is an anion. And what they do is they simply exchange the cations and anions. So it becomes AD and CB. It is as simple as that. The first kind is going to simply be a basic salt plus a basic salt yields a salt plus a basic salt, where you just have an exchange of cations and anions, a swapping, so to speak. So let's go right to an example where we see that it's an exchange. So you have potassium iodide plus lead-2 nitrate. Well, the potassium will go with the nitrate, and the lead-2 will go with the iodide. So you'll end up with potassium nitrate plus lead-2 iodide. So it's going to be potassium iodide plus lead-2 nitrate yields potassium nitrate plus lead-2 iodide. I'm not sure I said that right, but potassium iodide plus lead-2 nitrate yields potassium nitrate plus lead 2 iodide. So let's do some examples, and you can see how it's balanced, and you're balancing the nitrates on either side. So let's do lead 2 nitrate plus chromium 3 sulfate. So it'll be chromium 3 nitrate plus lead 2 sulfate, and then you simply balance the formula. Let's run through these quickly. I'll let you see them, and I will change the timing so it goes a little faster. So here are the reactants and products. And now we're going to look at gold 1 chloride plus magnesium pyrophosphate. So it'll be gold 1 pyrophosphate plus magnesium chloride. And there's the balanced chemical equation. So I'll let this run and see if you can, I want you to stop it, pause it, try to do the problem, and then push on after that. Okay, see what you can make of it. Now the next is going to be a more complicated double replacement, because the weak acid that is produced will break down to an acid anhydride plus water. Now, let's look at what an acid anhydride is just very quickly, very briefly. An acid anhydride is a nonmetal oxide, such as carbon dioxide, nitrogen oxide, dinitrogen oxide, nitrogen monoxide, etc. These are all acid anhydrides. And so you see that you have a strong acid plus the salt of a weak acid yields the salt of a strong acid plus the acid anhydride in water. So the weak acid that is produced breaks down to an acid anhydride and water. So what better way to explain this than to show you a particular example. Now just be careful. The states of the matter are not really important yet. So here we have a strong acid, hydrochloric acid, plus cobalt 3 phosphate, the salt of a weak acid. Okay, so what happens is the hydrochloric acid will mix and you'll produce the cobalt 3 chloride plus phosphoric acid. And the phosphoric acid is a weak acid that'll break down into diphosphorus pentoxide plus water. Now, you take that, you have to balance it, and then you take that balanced equation and you plug it in for the phosphoric acid. So you're going to balance this as is shown here, and then you'll substitute the acid anhydride in the water and the water for the phosphoric acid. And then you'll do a little fine-tuning with the balancing, and you'll come up with a final balanced equation. Now, I'm going to give you 3 additional problems just like this and see what you can do with them. Okay? And I'm simply going to go to the next set of slides that explain the next type of double displacement reaction. Good luck. So let's look at a different type of double replacement reaction called a neutralization reaction. And really, the neutralization reaction, an acid plus a base yields a salt and a water. The A and D is combining, and the C and the B is combining. So you're going to be taking an acid and a base and neutralizing it into a salt and a water. So you make the acid and the base harmless. So it's called a neutralization reaction. So let's look at an example of a neutralization reaction. Now remember, the ions are exchanging, and you always form water, and you always form a salt. So you're getting rid of the H in the acid and the OH in the hydroxide. So here's an example of pyrophosphoric acid and cobalt-3 hydroxide. So you'll get cobalt-3 pyrophosphate, and then you'll have as well water from the OH and the H from the acid. So again, when you're doing certain single and double replacement reactions, it's good to write the water as HOH. It's easier to balance that way. It's a little trick. All right, so what I'm going to do is I'm going to give you a bunch of examples, and then we will come back to the next type of equations. So good luck. And make sure you take it seriously. Stop the video, try to do it yourself, because you're going to be asked to do it yourself on some quizzes maybe. When we get into stoichiometry, you may have to do some equation writing from scratch. So you're going to have to know this. So I would suggest putting the video on pause, trying to do it yourself, and then going to the next one. All right? Next time I'll see you will be with the next type of equation writing. Now we're going to talk about synthesis. The book may call it combination. Synthesis where you're taking either two elements or two compounds on the left as reactants, and you're creating a more complex substance on the right, where you're combining them somehow. Could be two elements making like hydrogen and oxygen making water, or something more, a little bit more dramatic than that. So you could have an element plus an element. So the first type of synthesis, A, the first type will be an element plus an element, is going to be a compound. And now I'll give you a bunch of examples. And the deal is I want you to go through the examples, and then I'll come back when we're ready to do the next type. Okay? So good luck, and I'll be right back. So the next type will actually be two compounds, making a more complex substance. And it's going to be a base anhydride and water. A base anhydride and water is going to form a base. What's a base anhydride? A base anhydride is a metal oxide. So if you take a metal oxide and add water to it, it's going to form a base. One thing that we'll do in class is we're going to manufacture magnesium oxide. If you take magnesium oxide and add water to it, you get magnesium hydroxide, which is a base. And you can test as to whether or not it's a base. So just remember that a metal oxide combines with water to form a base. And the next slide will be your first example. Go through the examples, put it on pause, try to predict the products, try to write the complete balanced stoichiometric equation from just the names of the reactants. Okay? We'll be right back after when we're ready to start the next set. Now the next type is going to be also two compounds making a more complex compound, and that's going to be an acid anhydride plus water. Now an acid anhydride is a non-metal oxide, and you're very familiar with acid anhydrides. You just simply may not have called them acid anhydrides before, but for instance, carbon dioxide, the whole respiratory thing is based on acid anhydrides. So there are some very common. Acid rain is formed when you combine an acid anhydride and water, for instance. So you have a non-metal oxide, which is an acid anhydride plus water, yields an acid. Now, what acid is formed? Well, carbon dioxide becomes carbonate, or sulfur dioxide becomes sulfite, and here are the combinations. You also have the reverse of this, where you have, for instance, you can do If I break down sulfate, when we see in decomposition, we'll see that sulfate breaks down to sulfur trioxide. And if I have sulfur trioxide in water, it's going to produce sulfuric acid. So that's how you know which acid anhydride, like for instance, what acid anhydride becomes what acid. So, for instance, if you look at the chart, carbon dioxide becomes carbonic acid. Sulfur dioxide becomes sulfurous acid. P2O5, diphosphorus pentoxide, becomes phosphoric acid, etc. So make sure that you have this chart in your notes for your test, for instance. And then we're going to do some example problems, and then we'll go over the next type of synthesis. There's one left. And then we're going to start decomposition after that. Okay, hold on. All right, the last kind of synthesis or combination will be two fairly complex reactants forming a very complex product. And that's going to be an acid anhydride plus a base anhydride. Okay, for instance, if I have a base anhydride, magnesium oxide, okay, MgO, magnesium oxide, and I combine it with sulfur dioxide. So I'm going to make magnesium sulfite. That will be the salts. So you need that chart again to know what acid becomes what polyatomic ion, etc. Or what acid anhydride becomes ultimately what polyatomic ion. For instance, let's do another one. If I have barium oxide plus sulfur trioxide, it's going to be barium sulfate. If I have aluminum oxide plus diphosphorus trioxide, I'm going to have barium phosphite or aluminum phosphite, whatever it is I said, I don't even remember. So, for instance, in this example, you have aluminum oxide plus diphosphorus pentoxide, and you're going to produce aluminum phosphate. Okay, so the diphosphorus pentoxide becomes the phosphate. So you're going to need to reference that table again. Okay, so I'll see you again. We're going to start decomposition the next set of slides. Okay, be right back. Now we're going to start decomposition, and the general format for decomposition is when you have a complex particle and you're going to break it down to two less complex particles. Now, that could be a compound breaks down to two elements, or it could be a complex compound breaks down to two less complex compounds. But the first one is going to be a salt, and you're going to need some kind of catalyst, and you're going to break it down to its elements. Now, the catalyst could be heat, whether or not it's a catalyst, that's debatable, or it could be electricity. Now, some books separate binary compounds that you can decompose with heat, and binary compounds that are more stable that you need electricity or a melt. You need to put it in the liquid state to break it down. So, but we're going to look at this in terms of heat or electricity. So we're going to combine the two. So the first one is actually fairly unstable. It's not a terribly stable substance, so you can use heat. It's going to be mercury 2 oxide, and you're going to break that down into mercury and oxygen. And you'll see some of the other ones will be more familiar to you. And I may break in to show you a few things relative to how to make special arrangements, for instance, to break something down with electricity. But I'll stop by periodically as the tape is playing. Water actually is a very stable substance and you need electricity. But it may surprise you, but water does not conduct electricity. So to use as kind of a bit of a catalyst, you've got to put a salt in. And oftentimes the salt they use is sodium nitrate. And so you make a solution of water and sodium nitrate, and you run an electric charge through it. You set up two electrodes, and you can produce hydrogen and oxygen. So they use electricity. Now sometimes you have to make a melt, and then you can break it down using electricity. For instance, if I wanted to do sodium chloride, for instance, you can't put sodium chloride in water, or you can't do it as a solid. So I have to actually melt the sodium chloride, and then the sodium chloride, the melted form of sodium chloride, can conduct electricity, and then I can break things down to sodium and chlorine. Okay, so that's water, and then some other ones like sodium chloride or ionic compounds, you have to make a melt. You got to make sure you have perfect conditions. Maybe you can't have air, obviously, because you would decompose the sodium and chlorine into a variety of different substances. You'd burn it, so to speak, quote unquote, burn it. So you have to use a nice environment, maybe a noble gas in there in the melt to successfully separate the sodium and the chlorine. And so we'll continue with this where we left off with the water. This is a little bit like Fantasyland. It's going to be very difficult. This whole page is of salts. And it'll be very difficult to put them all in melts and run electricity through them. Some will happen, some will not. But the idea is that it has to be in a liquid form. It has to be able to conduct electricity in order to work. Okay, enough said. The next type of decomposition is going to be an acid. If I heat an acid, I produce an acid anhydride in water. So let's say it's sulfuric acid. Look at your chart. Sulfuric acid has sulfate in it. So sulfuric acid will break down to sulfur trioxide in water. You always get water. So an acid breaks down to an acid anhydride and water. Okay, I'm taking a complex substance, an acid, breaking it down into two complex substances, but a little bit less complex. So let's look at some examples of this. Okay, we're actually almost finished. Another type is going to be a chlorate. I can decompose a chlorate. One of the more popular chlorates we use in chemistry is called potassium chlorate. And that breaks down into potassium chloride and oxygen. It's an oxygen generator. And for that particular one, you use manganese dioxide as a catalyst. Oftentimes these need catalysts in order to break them down, not necessarily for the reaction to run, but just so the reaction doesn't run too quickly oftentimes. So, but manganese dioxide is a very common catalyst, especially for breaking down potassium chlorate, and that's what I have here. So I have potassium chlorate, and I'm going to break that down to potassium chloride and oxygen. So a chlorate breaks down into its corresponding chloride, magnesium chloride, potassium chloride, barium chloride, whatever, and oxygen. All right. So I'm going to let you do some problems on your own and see how many of them you can do. But again, put it on pause and see how many you can do. The next one is going to be a base. If I have a base and I heat a base such as magnesium hydroxide, what you're going to do is you're going to convert it to water and the base anhydride. So I could actually boil off the water, but it's water that I'm boiling off. So I am converting it to water, and the base anhydride is left behind. So magnesium hydroxide, I could boil off the water. There's the water, and I have magnesium oxide left behind. Okay, and I'm going to let you do some example problems. All right, be right back. All right, the last kind of decomposition is going to be, I can break down carbonates. Oftentimes, the early production of cements and concretes had to do with the breaking down of carbonates. A carbonate will break down to its corresponding oxide and carbon dioxide. For instance, calcium carbonate will break down to calcium oxide and carbon dioxide. The first one to write me a nice little half-page report on what that has to do with early building materials, I'll give some extra credit to. But that's one of them, where you take a carbonate and you heat it, and it breaks down into its corresponding metal oxide and carbon dioxide. Now I'm going to let you do some example problems, and I'll be back with combustion, our last type of chemical combination or chemical reaction. Now, up to this point, we've had several types, several subsets, several types of single displacement, double displacement, decomposition, and synthesis or combination. But with combustion, there's only one kind of combustion. You have a hydrocarbon, and you combine that with oxygen, and it produces carbon dioxide and water. Now, this is the careful thing. Very, very rarely will you get this as a perfect reaction. You get a lot of byproducts, a lot of could be cancer-causing byproducts called carcinogens. If I have a flame, for instance, a methane, and it's not a beautiful blue flame, but there's yellow in there, that means that not all of the methane became carbon dioxide and water. Some of it became byproducts or intermediate products. So one of the problems with combustion is to produce pure carbon dioxide and water. Oftentimes it's nearly impossible. One of the problems with an automobile and the internal combustion engine is that it's hard to, you produce carbon monoxide, you produce other, pollutants in the production of the carbon dioxide in water. If it was only carbon dioxide, that'd be one thing, but there's a lot of other things that are produced. So oftentimes combustion can be a what quote unquote dirty kind of chemical reaction because you get a lot of side products as a result of that. So now what I'll do is I'll let you do, I give a lot of examples, a lot of problems, like, 15 or so problems, examples of combustion. So you got plenty of work to do. Again, put it on pause, see if you can write the stoichiometric or the complete balance formula equation, and I'll be back to wrap up. Okay, that finishes the video. Good luck on your test. It's kind of a long video. It's about an hour and a half, but you'll do very well. And just go back and look at parts of it again, whatever your weaknesses are. So good luck on your test, and goodbye.